So good evening. Welcome to the 2025 Freeman Lecture, hosted at Wentworth. So welcome to Wentworth, all of you. My name is Gautam Das. I'm the Program Director for Civil Engineering, Biomedical and Biological Engineering, and you're in the Civil Engineering building. We're up on the 4th floor over here. I don't know why they put Civil Engineering, but up on the 4th floor, but we are on the 4th floor. We also have our Associate Dean, Anuja Kamath. I'm sorry, as she was eating, I kind of had to point out to her. So we are happy and privileged to have the Freeman Committee on the occasion of its 100th anniversary here at Wentworth, 100th anniversary. The Freeman Committee was established in 1925 to honor the legacy of John Freeman, one of the New England's most influential civil engineers. His pioneering work in hydraulics, public water systems, and dam design helped to lay the foundation for modern civil engineering infrastructure. In forming this committee, the Boston Society of Civil Engineers sought to foster dialogue and scholarships in the field which Mr. Freeman devoted his life. In recognition for the 100th anniversary, I would like to introduce the Freeman Committee members. First, I'd like to introduce our chair, the incredible Karen Kelly. From CDM Smith, Dr. Eric Adams from MIT, Steve Estes from MWRA, Stuart Kane from Alden Research Laboratories, Peter Shanahan, I hope I pronounced it right. He's not here. Peter is not here. Okay. Amy Mueller's here, I know for sure, from Northeastern. Kurt Pennell from Brown University. Paul Kirshen from UMass Boston. And Paul Matheson from WPI. John Lamonte from Tufts University. And finally, me, Gautam from Wentworth. So as we commemorate this centennial milestone, let us reflect on the enduring relevance to the Freeman Committee's mission to promote excellence in civil, environmental engineering, and to support the public good through the advancement of science and practice. Thank you again for coming here at Wentworth. I will hand it off to Emmanuel, the EWRI chair.
Thank you. Good evening, everyone. My name is Emmanuel DeAndroid, and I am the current Environmental and Water Resource Institute Boston Chapter Chair. The Boston Society of Civil Engineers section of ASCE, otherwise known as BSCES, fosters the professional development of its 3,400 members and their organizations by offering diverse technical lectures in various disciplines of civil engineering, legislative advocacy, public outreach, and awards and scholarships to deserving recipients. Our efforts help our members advance their careers and maintain a competitive edge in the global economy. All of this is made possible through the efforts of member volunteers who are active partners on our 9 technical groups, the Government Affairs Committee, Outreach Committee, or as liaisons to 10 student chapters. I encourage you to visit our website and find out how you might become an active member of the Society. Next, I would be remiss if I were to not thank our generous society and program sponsors. Without their support, BSCES would not be able to undertake the wide variety of technical events we conduct each year. And I will not bore you reading the numbers. The names of, you can see them on the screen. Here are the society sponsors. Move forward, you have the program sponsors. A few more. And finally, with that, I'm going to pass it on to Paul.
Good evening, everybody. Thank you very much for coming out. Last year was the warmest year on record, and the climate's only going to continue to change. And it's only going to impact hydrology. So tonight we have 2 experts, climate scientists, to talk to us about them. The first one is Matt Barlow, University of Massachusetts at Lowell, and the second is Bruce Anderson from Boston University. Matt's going to start talking mainly about inland impacts, and then Bruce is going to talk more about the coastal impacts. I've worked with each of them for decades, and they're truly knowledgeable in this field, and we're very lucky to have them with us. So why don't we go ahead, Matt?
Thank you very much. Appreciate being invited. It's an honor to be here, especially on the centennial celebration. No worries. It's better than if I tried to do it. Okay, great. So we're going to try to tag team this. So just a quick slide or two about what I do. So one of the things that I research is the dynamics of extreme precipitation, what causes different kinds of extreme precipitation events in New England, and how well are current climate models able to capture those events. So this is just showing you on the left 4 weather patterns associated with extreme precipitation from observations, from what actually happens, and what they look like in a climate model. And without getting into the details, that's basically what the jet stream is doing in these different kinds of events. So you've got kind of 4 jet stream patterns that are important in the real world. And I picked a good climate model. It's pretty much capturing those jet stream patterns as well. And of course, if we're looking to climate models for a view of the future, we want to make sure that they understand why these events are happening. I've also, as Paul alluded to, been involved in different climate assessments at different levels over kind of a long period of time now. I think if I get one more, I get a free coffee at Dunkin'. So looking forward to that. This is a brief history of milestones in climate science. I've been asked not to give a detailed overview of 150 years of climate science, but I did want to point out that the society was founded, I believe, in 1848 or so, which is actually still not older than the greenhouse effect, the theory of the greenhouse effect. So along the way here, I want to point out some of the times that we've learned things about climate science because it affects what confidence we have. There are some things we have high confidence in happening and other things we're less confident. And those kind of relate to how closely those things are related to fundamental science. So probably everybody here is familiar with the greatest hits of Fourier series and Fourier transforms. You may or may not be aware that he was the first person to put forward the greenhouse effect, the theory of the greenhouse effect in 1824. And just a little shout out to Arrhenius, who did the first calculation for the doubling of carbon dioxide, which you may have heard people talk about in climate change. What happens if you double CO2? And that experiment was first, or not that, the idea of that was first calculated in 1896, getting a pretty reasonable number. So I just want to emphasize that we've been at this actually for a very long time. Not me personally. In the interest of time, I'll jump forward 75 years, to bring in water. So the relationship of water and the hydrologic cycle to climate change is not a secondary or tertiary effect. It's a fundamental piece of global warming itself, which is part of why we have so much confidence in some pieces of our projections. So the water vapor feedback is from the 60s. It predates even me. And the idea of a more intense water cycle is from the 1970s. So those are some of the original predictions of climate change were related to the water cycle. And 2 key facts that you're probably very well aware of, but I'll just sort of highlight here is that, speaking casually anyway, warmer air can hold more water. So the warmer the atmosphere is, the more moisture you can have in it. Also, a warmer surface can result in more evaporation. So those are just basic physics. And they're part of why the hydrologic cycle is so closely linked to climate change. You already know it, so I'm not going to show you a little diagram of the greenhouse effect because you've seen it 1,000 times. You may have seen this as well many times, but also perhaps worth highlighting is that a fundamental part of the greenhouse effect is the water vapor feedback. Water vapor is also a greenhouse gas. It's the most important greenhouse gas. And so if you increase carbon dioxide, it makes things warmer. A warmer atmosphere holds more water. More water in the atmosphere makes more warming. And that's about 50%, about half the effect of carbon dioxide is through the water vapor feedback. So we don't get the potency of global warming that we're seeing without water vapor. So it's really built into that. That, of course, the warmer air holds more water is the Clausius-Clapeyron equation, just sort of schematically indicated here. Warmer, more moisture, or at least upper limit increases for moisture. And as you probably know, that's an exponential curve there. So a little bit of warming is a big increase in water vapor. Here, in terms of Fahrenheit, 1 degree Fahrenheit, every 1 degree Fahrenheit, you increase by 4% water vapor. And this, I'm sure you know, we've been increasing carbon dioxide a lot, more than 50% already over its pre-industrial. This is looking at our direct observations over the last 67 years. And you can see we really have not shown much indication of slowing down yet. This is looking over the last 800,000 years. The red ball there that unfortunately looks like a happy balloon is the current value. And you can see that in the industrial period, we've just shot up over anything in the last millennium, sorry, the last billion years or so. So if carbon dioxide goes up, of course, global average temperature goes up as well. The blue here is what's actually happened in temperature since pre-industrial. So we've already increased by over 1 degree Celsius. And we're staring down the choice, of course, of that high future emissions, which is hopefully unlikely, although over the last few months, it's looking more likely than it was, but hopefully still unlikely. But you can see there's a vast difference depending on what we do in the future with emissions in terms of temperature. And I just want to point out that 5 degrees, even 1 degree is a really big deal for globally average surface temperature. If you think about 20,000 years ago, there was about a mile of ice over us right now. That was a temperature difference of about 5 degrees Celsius between now and the last glacial maximum. So we're fiddling around with massive changes in the climate system. So we model these with computer models. And I also just wanted to point along the way, because we've been running these computer models for decades now, we can actually go back and check how well they've done, which gives us, I think, a good sense of how confident we can be in our future projections by seeing how well models have done in the past. And the red curve here is observations in terms of what actually happened. And the black curve is model projections. And the dashed line shows where the model prediction started. So these models were essentially starting prediction in 2000. So from 2000 on, there's no observed information in that black line. That's just what the models were predicting. And you can see the black line and the red line are a really good fit. So these are models that are 2 generations old now, back from 2004, a different world, a generation ago, and they're doing very well. So again, this is another piece of our confidence in some of these things, is that we understand the theory of a lot of this for more than a century. We see it in observations, and we're able to capture it in models. So again, water is a key piece of this. More evaporation leads to more water vapor, which leads to heavier rain. So if we've been warming already by more than 1 degree, we should expect that things have already changed. And in fact, they have. This is the change in precipitation on the heaviest 1% of days in terms of percentage change. So the Northeast there with the little plus 60, that's a 60% increase, more than half again as much in the amount of precipitation falling on those heaviest 1% of the days, 1958 to 2021. So over the last 70 odd years, we've already increased the amount occurring in these extreme events by half again as much. And that's just with a degree and change of warming over that period. You can also see that the Northeast stands out as a hotspot for the US in terms of increasing extreme precipitation. All right, what does that actually look like in events? This is Leominster from, I want to say 2 years ago, but now I can't subtract in my head. So 2023. And there was nearly 10 inches of rain in 6 hours, which we would typically associate with a hurricane, but was not a hurricane. We don't really need, now that we've supercharged our precipitation, we don't even really necessarily need hurricanes anymore to have these really exceptional amounts of precipitation. So this is really kind of a new risk environment in terms of heavy rainfall and flash flooding. These are the predictions for the greater Boston area. The report from 2022. The different colors there are different cities. You can see Boston, Lawrence, Hingham, and Maynard from 2000 to 2085. And different locations have different baselines of precipitation. This is the 10-year design storm, but they all increase, you can see, and they all increase relatively uniformly by more than a tiny amount. So not only have we seen already the big changes that we expect, but we're expecting them to go forward into the future. These are the projections for flooding. Small floods, design floods, 100-year floods, and flood frequency overall. And so by mid-century 2055, and you can see there's an uncertainty range there, but if we pick the middle of it, let's say a 10% increase in small floods, and again with an uncertainty range, a pretty substantial increase in 100-year floods as well. And I don't have a slide on this, but I think it's worth mentioning that people who research climate assessments and the way media portrays climate assessments tend to think that climate assessments are far too conservative. And you can ask my colleagues whether or not they think that's true. But there is a lot of evidence to suggest that when you get a bunch of scientists together and you ask them to agree on something that they may be picked on by their buddy scientists about, that they will tend to pick what they feel is completely defensible rather than what they actually might think is their best sort of professional estimate. And there's some more recent studies that suggest these numbers may be even bigger. One metaphor people like to make is that the atmosphere is like a sponge in terms of its water holding capacity. So the bigger the sponge, the more water it can hold. A bigger sponge full of water, you squeeze it out, you get more water. That's your intense precipitation. But if the sponge is not fully saturated, it can also absorb water really well. So this is sort of the other side of the coin. We expect more intense precipitation, but we also expect more periods of intense dryness. This is the sort of water whiplash you sometimes hear people talk about, where we're alternating between periods of really heavy rainfall with periods where it's much drier than usual. So we expect global warming to increase both wet and dry extremes. So water whiplash, sorry, the droughts escape from the little box there, but it means paradoxically that we expect most places, typical places, to have both more floods and more droughts at the same time. And that's why I called out the hydrologic cycle paper from the 70s, because that's exactly what they were looking at. Tsuki Manabe, I think I forgot to mention, he got a Nobel Prize a couple of years ago in physics for that. So this idea of an enhanced, accelerated, intensified hydrologic cycle is an old, very basic piece of climate change, and that's one reason why we have so much confidence in it. This is a picture from Attleboro from August 2022. This is a reservoir, not perhaps fully serving its function at this particular time, but giving you a sort of a visual example of what we mean by this kind of water whiplash. And here's just in words, Boston from last year, sort of famously, many of you may have sort of noticed this along the way, especially in the fall, but January was near record wet, followed by February, which was near record dry. And then it continued to sort of ping back and forth through most of the year. And the whole year actually wasn't that far from average, even though it had some extraordinary dry periods in it, particularly the fall. If you were here last fall, you may have noticed wildfires making a local appearance, unfortunately. So September, October, and parts of August and November were really dry. But by the end of November, the year was actually at average because it's alternating between these very wet and very dry periods. All right, so climate assessments. I don't want to spend too much time on this because you may know a lot about this already, but a lot of science, well, really science proceeds by individual papers, individual studies. But climate assessments are the idea that for some of these bigger problems, we need to assess the science. So when we're doing a climate assessment, we're also trying to figure out what we're confident about and what we're less confident about. And we reserve our highest confidence where we again have this agreement between what we understand, the theory, what we actually measure, the observations, and what we're able to reproduce and in this particular case, predict in a model. So we have the highest confidence where we have that agreement. And then these assessments go through the process of looking at all the peer-reviewed literature and identifying areas where, for high confidence, where there's agreement across multiple studies, multiple groups, and well-established methodology. So the upside of this is that you get a very authoritative assessment of what's going on. The downside is it does tend to be very conservative and it's a very slow process. So I'm going to show you a couple of bullet points from the US National Climate Assessment, which just went through its 5th iteration, so NCA 5. The National Climate Assessment is the basically the US government's climate assessment, official climate assessment mandated by Congress. At the international level, it's the IPCC, and then the NCA is the national version. I just want to highlight a few things. You may be very familiar with these already, but just to really emphasize that there are a bunch of things that we're already quite confident about. Increase in severity, extent, and frequency of multiple types of extreme events. Rainfall has become more extreme in recent decades, especially east of the Rockies. Very high confidence. Of note, especially for us on the northern end of the range, hurricanes have been intensifying more rapidly since the 1980s with high confidence and causing heavier rainfall and higher storm surge. Again, high confidence. And that high confidence is coming from our understanding across all of these pieces of evidence, the burden of evidence, as well as the fact that the basic sort of physical understanding is very old at this point. Heavier rainfall events are expected to increase, very likely, very high confidence. And then sort of presaging Bruce's part, the severity and risk of coastal hazards are increasing, very likely, high confidence, driven by not just the pieces we've been talking about, but bringing in sea level rise, which Bruce is going to talk more about, which is also a fundamental prediction of climate change. You don't warm the climate without increasing the sea level, which increases flooding, erosion, and and acts in concert with rising groundwater. And then I think this is my last key message from the NCA 5. The Northeast continues to be confronted with extreme weather, most notably extreme precipitation, which caused problematic flooding. So not only is this a general expectation, but we're really kind of a hot spot for these increases in precipitation. Slight sidetrack here, but I think maybe it's worth worth highlighting. Often when we talk about risk, we talk about return periods. We talk about what's happening to the 100-year storm or the 10-year, 24-hour design storm or things like that. And I just want to point out that there's this kind of devil's bargain between the fact that if you want to estimate, say, a 100-year storm, you would like more than 100 years of data. You would like as much data as possible because that really reduces your uncertainty in the estimate of that 100-year storm. But the longer period of data you look at, the more out of date that estimate is, and they go right hand in hand. So for example, for those of you who are fans of the NOAA 14 Atlas, which is the sort of US standard for extreme precipitation, for the Northeast, a common period they use is 1950 to 2012. So that's a pretty long period. You feel pretty good about your estimate of extreme events, IDF curves and things like that. But if you assume that there's a trend, which there is, you're looking at the middle of that period. That's the risk that you're looking at. So when you use the estimates from 1950 to 2012, you're getting you have a lot of confidence in your result as it would look in the 1980s. So pretty badly out of date. As those of you who work with NOAA 14 or DEP also works with NOAA 14 Plus, they have their own sort of special sauce to try to account for this. But NOAA 15 is the replacement, because NOAA, of course, is very well aware of this. So there is a replacement in process that explicitly accounts for this as well as future change. NOAA 15, which is in currently pilot preliminary form. And I think it's maybe fair to highlight there are concerns about whether this actually will now get finished, considering all the sort of federal issues that are going on. But it is certainly a critical effort. All right, one more topic, and then I'm going to sort of wrap it up to hand off to Bruce. Hurricanes, I think, it's reasonable to say, are kind of a big deal. We don't get hurricanes that often here. We get their remnants fairly often, and most of our highest extreme events in terms of precipitation are due to hurricanes and their remnants. So they are really important in the Northeast for extreme precipitation. And there are some things we know about hurricanes with a fair amount of confidence, based again on our basic theory, and others that we're less certain about. The things that we are certain about is warmer air holds more moisture for rainfall, so the rainfall is going to be more intense. We also know that warmer oceans, the evaporation from the warm ocean, the latent heat release from that evaporation, that's basically the heat engine of a hurricane. They basically run on warm ocean temperatures. And oceans are warming along with the atmosphere. And then the last piece that Bruce will talk more about is if you raise sea levels, the storm surge, even if the storm surge doesn't change, it's riding on top of a higher level. Having highlighted that ocean temperatures are important, and this is perhaps related to why we're a hotspot for extreme precipitation, but the Northwest Atlantic is one of the fastest increasing ocean temperature areas in the world. So unfortunately, the sort of fuel for hurricanes we're sort of building up locally. One of the things that limits our parts of our understanding about hurricanes is that they're relatively small spatial scales compared to the type of spatial scales that our current climate models resolve. So if you think about a picture like a digital screen, it has pixels, and the smaller those pixels are, the better you can see the image. For current climate models, the pixel size of the hurricanes is a little too small to be nicely resolved in our models. So we have ways around that require additional modeling, but it does require an additional step. It's computationally expensive, so there's less of it. So there are pieces of hurricane changes that we're quite confident in, and other pieces that are sort of limited by some of these spatial scale issues. So just to wrap up my piece of it, I just want to highlight again that there are pieces of climate change that are very straightforward and we're highly confident in. There are more complex pieces that we're also pretty confident in, but are more complicated physical processes. And then there are pieces that we're just less certain of. So again, high intensity rainfall, the enhanced hydrological cycle, the hydrological whiplash, sea level rise, very confident. Other things we're confident of but are more complex is the potential for stronger and slower tropical cyclones, meaning hurricanes and their cousins, seasonal shifts in precipitation, which I haven't talked about, but which can be very important, compound events. So if you have overland flooding, if you're at the coast and there's a river nearby, you might have overland flooding, river flow flooding, storm surge, and the storm surge backs up the river. So the more you sort of supercharge all these things, the more likely you are to have a compound event. And threshold events, which is where the behavior changes markedly over some value. Keep pushing everything up, you keep getting closer to those thresholds. And then again, there are things that we're less certain of. For instance, the average wind speed of winter storms, what sometimes are called nor'easters locally when we're trying to pretend we're all pirates. But that's a big question, is what's going to happen to nor'easters in the future. And there are some opposing factors that are influencing nor'easters. So we're just less certain of some of those pieces. But just because we're uncertain about some things doesn't mean we're uncertain about everything. And I'll just end again by highlighting that point. Even if nor'easters didn't change in strength, even if their wind speed stayed the same, we know that they're going to come with more intense precipitation, and we know that their surge is going to happen over top of the sea level rise. So when we're thinking about climate change, we always have to sort of balance off what are the pieces that we know, and not let the fact that there is some uncertainty, which people often focus on and is valid, not let that and end up with us feeling like we can't say anything. All right, and I will there hand it off to Bruce.
Thanks a lot. Thank you, Matt. I was going to say, we're going to have questions after. So after Bruce speaks, we're going to have a Q&A session. So thank you very much. Here's Bruce.
I'll just echo the fact that I really greatly appreciate the opportunity to talk to you. I'm going to actually try and walk around. So I'm going to use a clicker. We'll see how effective this becomes. It just allows me to look at what I'm actually talking about. Okay, so importantly, there's this concept. So somehow this is supposed to, there we go. That there is this concept that we, even if we're less certain about what's going to happen to winter storms, we know that they're occurring over higher sea levels. So we certainly with storms, we're going to have the precipitation effect, so overland flooding. I'm here to talk about what's happening along the coast. Okay, so what are some of the things we know? Well, we know sea level is going to rise. So this is a set of estimates through the years based upon various what we call emission scenarios. That's not important. How much greenhouse gases do we put into the atmosphere over the next 100 years or so? And for two purposes. One, because it's in your sort of window of for engineers, I'm going to focus on this 2050 period throughout this, just because it's not too far in the future. This is design windows for you guys. The other thing to note, though, and if that one doesn't show up here, what happens to sea level is baked in up through 2050. It really doesn't matter what we do with regard to emissions. Doesn't matter whether we crank out emissions and go with what's called the business as usual, whether we diminish emissions and go to some stabilized or even go to zero emissions. This is baked in. That's going to be your sea level rise by 2050. Okay, so that's what you guys need to plan for. So that's why I'm going to focus most of the talk on that period. A lot of it's going to be either based upon 2050, or you'll see images that use a 21-inch sea level rise as a base sea level rise. Okay, so that's where we're focusing. Okay, just some background. Why is sea level rise going to occur in the Northeast? Well, there's some, so that's that. There's some common things that people know. Certainly Greenland's melting, and so that's pumping water into the ocean. Antarctica's melting. Thermal expansion, water gets warmer, it expands. And then in our region in particular, there's sinking ground level, both as a rebound from the last ice age, and we're also drawing out groundwater. But there's two local particular effects that aren't captured here. One is gravitational redistribution. So when Antarctica's ice melts, that was a gravitational source for the ocean. There is a big pool of water sitting down by Antarctica through its gravitational pull. When that water melts, it redistributes, but it also loses its gravitational pull, and there's going to be a massive redistribution of water in the ocean from around Antarctica to us. So there's a big shift of water just because Antarctica is losing mass. And that is so much mass that it's actually modifying the gravitational fields around Antarctica. So you'll notice that will also locally raise our sea levels. The other has to do with the Gulf Stream. This is the height of sea level locally, relatively high heights off the coast of North America. Here is Boston right here. And this is the separation, is the location of the Gulf Stream. It turns out that this is relatively warm waters. This is relatively cool waters. Locally, right now, we're under the influence of water from the higher latitudes, relatively cold water in our regions. More dense, lower sea levels. As this gets displaced to the north and is replaced by this warmer water from the south, sea levels go up locally. Not only that, the gradient or the variations in water from height here to here is a measure of the strength of the Gulf Stream. The stronger the Gulf Stream, the larger the drop. If I can get my little arrow between the reds and the blues. As the Gulf Stream weakens, which is an expectation, the drop between high and low sea levels is going to decrease. Again, what would look like this, with this being the water near the coast and this being in the open ocean, is going to go like that. And so all five of those are factors that influence our local sea level. And it turns out all five have about the same influence. No one dominates sea level rise locally. Okay? So that's the background around why we expect sea level rise in this region. Now let's see the outcomes. As was said, we could ask, well, what would happen to flooding in our region? I'm going to consider to start just the let's see if I can, oh, wrong button. There we go. The current 100-year flood or 1% flood, currently with a 100-year storm at high tide, the flood level is 9.2 feet above base, okay? Take that same storm, and the reason we're taking the same storm is that most of these flooding events actually occur in winter or associated with winter storms, and there's not a certainty on what's going to happen to the intensity of the storms. Precipitation will increase, which we just heard, but the strength of the storm, the wind fields which dominate the storm surge, that one's uncertain. So you take that same storm, you impose it on a raised sea level, and now we're looking at, let's go to 2050, not surprisingly, because the sea level between, this would be a low emission scenario, this would be a high emission scenario. The storm surge itself is nearly identical, but instead of occurring just 1% of the time, there's a 10-fold increase. So now instead of having let's say once every century, which isn't a great way to phrase it, but let's use that phrase, once every decade. Okay, so what would be hitting us every century, that storm will now, that equivalent storm, well, in fact, no, it will, the other best way to say it is, instead of requiring a 1 in 100-year storm to inundate, let's say, our defenses, which is what this is, our infrastructure is typically geared towards, now that's going to impinge itself on, or impose itself on us every decade or so. Okay? So that's the first thing. So this is what we've got to start designing for. If we then go and look at what locations are influenced by either the decadal storms or the centennial storms, certainly the waterfront or the seaport's not a great place to be. East Boston's not a great place to be. The financial district, over by the stadiums. And what will pop up is us in a little bit. I'll show you why. It doesn't show up here, but it'll show up in another figure. So those are the hot spots for these flooding events by 2050. Now, as we flood places, people live here, infrastructure is here. Whoops, I went backwards. We can go and calculate what percentage of the population is going to be directly influenced by these storms. Under the 1 in 100-year storm, 7% of the population. Sort of every decade, 4% of the population. We can ask the same thing about the buildings, about 10%, 5% of the buildings, 3% here of the buildings sort of once a decade. And again, though, these are very localized. So in some locations in Boston, this is across all of Boston, there's not going to be much impact because they're not on the coast. But those hot spots, for instance, the South End and the Seaport, 50, 60% of its population, 50, 60, 75% of the buildings are going to be inundated once every 10 years or so. That's what we're looking at with this sort of 21-inch sea level rise. Now, needless to say, this imposes a cost, and that's what's shown here. These are the size of the buildings is the loss per building. So where you have really big buildings or big circles, that's a single building that's worth a lot of money that's going to be affected. You see that certainly in the Seaport. You certainly see it in here. But what's going on here in the Back Bay? We didn't see a whole lot of flooding in our previous slide. This is from really unlikely storms that, were they to occur, would flood the whole Back Bay. Or whole South End, sorry, not the whole South End. Because if I can get an arrow, there is one conduit, I don't know why I'm not getting an arrow, between there and there, you'll see where the water comes in. There's one conduit that's high enough, but if it ever gets overtopped, this whole, like 80% of the South End gets flooded. So in this, at least by 2050, this is a highly unlikely scenario, but highly impactful if it were to ever occur. And because of that, there is the possibility, this is annualized, they account for, okay, it's not going to happen often, but if it happens once, it's so devastating that it actually shows up on this map. Come the end of the century, this place sees that once every 10 years. As I said, I'm only looking out to 2050. You look out to 2100, by the time the sea level rises that extra 50 years, this isn't just seeing it with the 1 in 1,000-year storm, it's seeing it in the 1 in every decade storm, okay? So there's obviously some financial costs to this. We can break that out in different ways. One is we could ask what's the annualized cost. And here we have for, again, mid-50 or 2050s, 21 inches of sea level rise. Per year, the biggest influence or the biggest problem we face is just the once in every 10-year storm. That's going to, just because it occurs so frequently, when you annualize it, you divide by 10, the annual impacts are actually the largest. That's the one we're just going to have to continuously deal with. And we're looking at per year, $300 million a year Boston's going to be spending if they don't up their defenses, okay? Were we to get the one in a 100-year storm, it gets up to somewhere 455 minus that 12 million, whatever that is, something like, let's just go with 425 million were we to get a 100-year storm. Now that's annualized. So that means that you take your 10-year storm and you only divide it by 10 years. You take your 100-year storm, you divide whatever the damage is by 100 years. When you look at the cost for a single event, though, that's when you really start to see the impacts. So here is, were we to get hit by a single 10-year storm, which is there, we're looking at $2.5 billion of damage in Boston alone. That's the greater Boston area. That's nowhere else on the coast. Were we to get hit by a 100-year storm with this sea level rise, we're looking at something over $5 billion worth of damage, okay? And so this shows you the cost per event. And I will say that it's not up here. You can break this out as to where is this cost incurred. About half of it's incurred in damage to infrastructure. Half of it is due to loss of property, like only 5% is loss of jobs, things like that. It's almost all in either your infrastructure is destroyed or your whatever's in your infrastructure is ruined, okay? And that's topping out at something like, the 1 in 1,000 is the purple one. Gosh forbid, that's $10 billion worth of damage from a single storm. And that's only from less than 2 feet of sea level rise, which is what we might expect within the design range of whatever you guys are now building, okay? So that's the cost, that's the impacts. Now, he was actually the science advisor under Obama. He said, we basically have 3 choices in the face of this. We can mitigate. Mitigate means to actually start to reduce carbon dioxide emissions and as well as other heat trapping gases. Hence, climate doesn't change as much. This does not work for us by 2050. I already told you, everything we've shown you is built into the system. It's baked in. That is our expectation for sea level rise, regardless of what we do over the next 25 years. There's simply nothing we can do about it. Mainly because temperature's warm, sea level keeps rising thermally. It's like the phrase I use is it's like an ice cube. You take an ice cube out, you put it down, it's in a new climate. It doesn't melt instantaneously. It just keeps melting as long as it's warmer. Antarctica is going to keep melting. Greenland's going to keep melting. As long as those keep melting, sea level is going to rise. So that sea level rise that I've been showing you, it's baked in at this point. Mitigation is not going to help us over the next 25 years. So then there's adaptation, which is what I'll talk about, and then there's suffering. So we sort of have for Boston a choice of 2, adaptation or suffering. So let's go look at what the adaptation is. It turns out that this was done. There was we were part of a group called, what was it? Well, that's Boston Research Advisory Group, which was under, what was it called? Yeah, Climate Ready Boston. And so they took all the results that we put together from the scientific community and started to look at its impacts on Boston. That's actually where a lot of this comes from. So if you look up BRAG, B-R-A-G, Boston Research Advisory Group, that was 2016, but none of this has changed. They redid it in 2022 as part of the Greater Boston Research Area Group. Go look that up. You'll see all of these figures. None of it's changed in the last 10 years. And they came up with layers of climate readiness. How do we prepare for this? And 3 of them are sort of built environments, and 1 is a social environment. They certainly recognize the need to prepare and connect communities. I'll show a few of those. We need to figure out what to do with our shores, particularly with regard to the impacts of sea level rise. We need to think about how we're going to build more resilient infrastructure, and we have to figure out how to adapt the buildings we already have, okay? And so they came up with, I think, 13 strategies, 2 or 3 for this, 2 or 3 for this, 3 or 4, 4 or 5. Some of them had to do with financial tools you'll see on there. How do we encourage more adaptive building practices, policy initiatives? They came up with a whole bunch. But this is sort of the map that they came up with, or the schematic is probably a better word for it. The color coding, if you remember, this is the social and community aspects. This is the sea level, the walls. This is something to do with new building, and this is adaptation. And so you might not be able to read it in the background, but there is a whole bunch of concrete steps, to use it metaphorically, to addressing each of these. And they went through and started to come up with design elements, particularly for these last three, purple, blue, and green, that would address many of the most pressing and immediate issues that will accompany hazards associated with sea level rise and increased storm surge frequency as well as intensity. So to end the sort of joint discussion, I'll just finish with this. We know that climate change affects all aspects of hydrology in Boston. We've talked about the changing precipitation leading to more flooding, enhanced evaporation leading to more droughts, and then obviously I just covered coastal flooding. But I think the take-home message, both from Climate Ready Boston, which is where I'm going to steal these three talking points from, is the following. Boston has dealt with, for its probably entire existence, climate risks. The key here is that we now have an ability to forecast that these will increase. We have an ability that our predecessors probably never had. We have an ability to understand what's being exposed to risk and what risks are changing. And if we get on top of this, Boston can thrive. As long as we take action to adapt its people, its communities, neighborhoods, but also its economic, cultural, economic assets, including infrastructure, hardscaping, soft landscaping, we can make it. And the key here is bold. It requires bold and creative action that'll maintain the city's vitality and livability, which is, I think, for many of us, why we're still here. So with that, I'll finish up. I think we'll both be here to take questions. And other than that, thank you very much.
You can yell at yourself.
Okay. Yeah, I guess we're just supposed to stand up here and take questions.
I mean, I gotta know about the one pump. Is that
It's-
an open channel or a sewage pipe?
Oh, it's what is that one? Let's see if I can get back to it. It's where 93, you know where the 93 tunnel dives as you go 93 south into it's right there. 4-point channel. What? There you go. So I don't know what I couldn't get the pointer, but yeah, that's it. That's the low spot. And if that ever gets breached, yeah, well, you probably do better than I do. Yeah, sure, you probably worked.
Give me a mic for the questions so everybody hear.
Actually. Oh, okay. Yep. Maybe you could run the mic.
I can do the mic, yeah.
I'll keep that one here now. Just pass that one around and we'll keep one up here.
Thank you for the presentation. I have a question regarding these IDF curves, design curves, we call them. And we know that there's a non-stationarity in the system now. So what's the message that you would like to give to the engineers who are designing actually things to handle these non-stationarity curves? It's not only about that, but the intensification of these events, extreme precipitation events. We usually look it from the daily scale, but now we know that hourly scale precipitation extremes are increasing highly. And the typical example was 2023 precipitation in New York, where the drainage system was not capable to handle the extreme precipitation. So the questions for both for the engineers and for the scientists also, how to handle these situations. We know these things are happening and these are things are going to increase further.
Yeah, I'll take a cut first. And first I want to say, if you found that presentation a little depressing, which I always do, I assume looking out at a bunch of engineers that you're also thinking job security. So I just want to point out that there's a positive message in this and in that question as well. So this is probably not a helpful answer, but I think I would say that it is not best practice to use a historical estimate of risk of extreme precipitation. You know, if you're just using it out of the box, I don't think that's good practice anymore. There are lots of techniques people have devised for accounting for the non-stationarity. So for instance, I believe Mass DEP takes the NOAA 14, which is an estimate, and then they use maybe the 90% threshold or something to sort of rule of thumb or, you know, kind of estimate the effect of the trend. But I would certainly assert that estimating the effect of the non-stationarity, even imperfectly, would be much better than simply ignoring it. So I think that's the reason why there will be hopefully a NOAA 15, is that then everybody can use the same product with the same known limitations. But until that happens, I would say that picking one of the many ways out there to estimate the increase would be better than not. I don't know if that helps.
Question? There you go. Barry.
So you talked, I guess this is a Matt question. You talked about the physics of climate change and a number of factors. Could you comment a little bit on how the trajectory of the jet stream is affected by climate change in terms of the magnitude and variability? At least qualitatively.
Well, we've written some papers, and then people have then made a habit out of writing papers about it that say we're wrong. So keep that in mind. That's a hot topic. So I think that is one of the big questions, is what will happen to the jet stream. And I think part of the problem is if you took all the continents away, it would be a pretty simple answer, and the jet stream would probably weaken and move poleward. But failing taking all the continents away, it proves to be a very difficult question. You've probably heard people talking about maybe a wavier jet stream, or our favorite hobby horse, maybe the stratospheric polar vortex, is doing something in the short term with Arctic amplification. But I think the sort of the assessment answer would be is there is not a consensus on what's going to happen to the jet stream, because it's governed by multiple factors, some of which are going up and some of which are going down. So that's one of those, I think, sort of uncertain ones. But I imagine Bruce would like.
Oh, Bruce
will answer it.
No, I won't answer it. I will just reiterate that, in fact, this is one of there's a few things. What's going to happen to clouds is one of the greatest uncertainties. But another one is what's going to happen in the mid-latitudes with the jet stream. It's just, you can run different models with different results, and you can do it theoretically, you can do it numerically, you can use observations depending on how you define the jet stream. There really is no definitive answer on what's going to happen to the jet stream at this point.
Question? Okay, actually, I have one. Matt, you showed in one of your images that in mid-century, the discharge of the 100-year storm could actually decrease. You know, in the end of the century, they're all increasing, but you showed a range where it actually decreased by 30%. Why could that happen?
Yeah, I think it's a combination of sampling uncertainty and natural variability. Yeah, so it can. So there are these big ranges here. Yeah, -10 to +35. And I think what's going on there is that the climate system is always varying, year to year and century to century, and that variability is stronger in extreme events because they occur relatively infrequently. So if you look at any given period of time that's relatively short, this is like 30 years out, there's always going to be some chance you'll get fewer of them just because of luck. But the message that I would emphasize there, and I'm sure you wouldn't disagree, is that you're preparing for the high range, not the low range. So you can hope for the low range, that would be awesome. But you have to be, I think, prepared for the high range. And the same thing is true of hurricanes. Maybe to provide a really concrete example, there are natural periods of decades or more when hurricanes are less frequent in the western part of the Atlantic as the oceans go through their natural cycles. And that happens without human interference at all. You have decades where you have a lot of them and decades where you have fewer purely naturally. So climate change is on top of that. So if you focus on these, what from a climate perspective is a short period, like out to 2050, you always have some chance that natural variability is going to oppose climate change, but you have an equal chance that it's going to add to it. And then from a design, standpoint, probably you want to consider the latter. Does that?
Yeah, no, I was thinking it might be due to the fact that maybe it's warming up faster than the rainfall is increasing. So maybe that's due to evapotranspiration, but I don't know.
It could be. I think probably not for the 100-year event, probably for the less frequent events, but that's possible.
Another question? Yeah. Paul.
Just a couple quick questions. One is just the Gulf Stream and the transitions potentially anticipated. Can you just comment on what's anticipated for the region up here as well as possible for the Gulf Stream? And I guess the only one I'll add in too is as we look at the analyses looking towards the cost changes in the flooding conditions anticipated moving into the in the Boston region and where you got those costs from, in terms of the technical analysis, is it just the details of both the basic rise as well as different surges that are included in there and how that was technically analyzed?
Okay,
Just to clarify.
I'll ask you-
Sorry if I missed it.
No problem. I'll ask you to repeat the second question in a second, but I think I'm going to deal with both of them. So, in fact, in the BRAG, the Boston Research Advisory Group, we never dealt with the ocean environment. In this most recent one, prior to doing it a second time, we actually went out to the greater Boston area and, in fact, queried communities. And it turned out that one of the biggest holes in the original BRAG, which is the Boston Research Assessment Group's climate assessment for Boston, was the marine environment. So we added in a special section this time around on the marine environment. And it actually was much more difficult than we thought because we had to consider not just the physical aspects, but also the chemical, biological, and geological aspects. But that said, we did do it. And so I did have to go and actually start to assess what the expectations were for the Gulf Stream. Okay, so why would the Gulf Stream change? The Gulf Stream potentially could change because portions of the Gulf Stream are supporting deep water formation in the high latitudes of the North Atlantic. As the globe warms, you get freshwater input into the high latitudes of the North Atlantic. It becomes fresher. It also gets warmer, less dense, doesn't necessarily have to sink to the bottom of the North Atlantic, doesn't necessarily need to sustain what we call the conveyor belt or the Atlantic Meridional overturning circulation, that less deep water formation. So the component of the Gulf Stream that feeds into the high latitudes of the North Atlantic potentially could weaken. Now, what I always ask my students is, well, does that mean the Gulf Stream is going to shut down? No, 80% of the Gulf Stream is part of a wind-driven gyre circulation. Only 20% actually plays into deep water formation. So potentially the Gulf Stream could shift or weaken by about 20% at most. through the shutdown of that deep water formation. So there'll always be a Gulf Stream, but there is the potential that it can weaken. And so if the Gulf Stream weakens, it turns out where it goes off of Cape Hatteras, that is this northerly latitude is influenced by the strength. The stronger it is, you know, the Coriolis force, the more it's going to get diverted to the right. It diverts at a lower latitude. Weaker Gulf Stream, it actually starts to extend further up the coast. So a weaker Gulf Stream will move further up the coast. It also, as it moves up the coast, it intrudes on the portions of the the currents from the north. So that's the two characteristic expectations is the Gulf Stream is going to weaken because the portion, that 20% that feeds into deep water formation is going to reduce the strength. And then secondly, because it's weaker, it's not going to jet out into the open ocean as far south and might shift slightly into our region. So those are the two expectations. We're going to, in our region, come under the influence of the warm water from the Gulf Stream more frequently. So does that get to the question about the Gulf Stream?
Hopeful, yes.
Yeah. Now, what was the second question?
Should I pass it? Does anyone else want to ask, or you want me to continue? Okay. The question was looking basically with the cost estimates and the considerations regarding sea level rise and the impacts on the interior city of Boston. Just in terms of that analysis, there's both the basic sea level rise, but there's also kind of the rise in, due to hurricane storm surge. And I'm just wondering what was the analysis and the approach to quantify that, and what are the
because at least for almost all of these, because there was so much uncertainty about the change intensity of the storms, not the precipitation that accompanies them, but the strength of the winds, because that's what determines the storm surge. There's also uncertainty about what type of storms we're going to get. Are we going to get nor'easters? Are we going to get, what are the ones that clippers? I think there's about 4 named types of storms that influence the Northeast. I don't know what they're all called, but there was just so much. The scientific community just throws up its hands at that point. So they used they did use the same return rate of storm surge. So the 100-year storm surge was the same, but then they imposed that on a higher sea level.
Thank you.
Yep.
No problem. Thank you. I also had a question about the economic analysis. So I think like these graphs get a good picture of the cost of inaction, the cost that we pay if we do nothing. But is there estimates for one, how quickly, or the price that it would cost upfront to start protecting buildings, or estimates for what the amount of damage or cost of damage would be if we did start protecting buildings and infrastructure now?
It's a great question. Certainly none of that was done in this analysis that I've been drawing from. I'm trying to think whether when we did the BRAG, anything moved cost benefit analysis. You want this?
Yeah. When you, anyone here from Climate Ready Boston, the city of Boston? Okay, so thank you. No, so they talk about the cost to protect the entire 47-mile coastline of Boston might be $5 billion, $5 to $6 billion, and that would be using green infrastructure where possible, but also traditional flood walls where they couldn't put in nature-based solutions. Also, the plan is to, Bruce talked about this flood pathway into the south end. Well, also certain flood pathways like on Border Street in East Boston, which are problems now. So the strategy of the city is to initially fill in the most earliest flood pathways first. What's going to flood soonest? They'll fill them. They'll protect those, and then silver goes up. They might make them higher, and then fill in the next area. So they're going to expand it over time as the climate changes, and that's actually a pretty good approach because that's like adaptive management, and they can adjust as the climate changes, which is a good way of dealing with the uncertainty. And also it means we don't have to spend all the money up front. We can just spend it over time, next 20 years. If they were going to build like this massive, offshore barrier from like Winthrop to Hull, okay, that would have been like $10, $12 billion. But they have to sort of pay all that money up front by trying to plan for an uncertain climate. So that's sort of a partial answer. But the benefit cost ratio for this adaptation along the coastline is like 4 to 5, 6 to 1. So it's if the city can afford it, which is always a problem, and if the region can afford it, it certainly could be beneficial.
Can I piggyback on that question, which I really liked? Has anybody estimated the economic benefit of these changes? Right, because a lot of these proposed changes have lots of positives, some of which are harder to quantify than others. But any economists here? No, economists make stuff up all the time, so I don't know why they couldn't do that. But there's a lot of economic benefits to different communities in Boston. Be better public transportation, public health benefits. You're not missing school, you're not missing work, not problems with emergency services. Do you know if anybody has tried to estimate actually the benefit, the sort of the offset of you treat it as an investment rather than a cost?
They've estimated the damages avoided to buildings and loss of business. Okay, so they've estimated those benefits, and essentially that's where those numbers came from.
Yeah, I was thinking on top of that.
And then on top of that, there are these co-benefits, like providing open space in a community like East Boston where there's not a lot of open space. So there's a lot of social benefits. And then if they use green infrastructure, they can get past the permitting hurdles. There's all sorts of ecological benefits. And so you can use the approach of ecosystem services to put numbers on these. I don't think anyone's really done that, but it would be a pretty straightforward calculation to do. A lot of these things we want to do in terms of adaptation are probably things we want to do anyway to improve life in Metro Boston. But Karen, how much time do we have? Okay, so look, this is a pretty good opportunity because we have some climate scientists here with engineers, and I'm also a civil engineer, and as you know, we've always designed to a certain value, like the 10-year, 24-hour rainfall, the 100-year storm. But as I'm pointed out now, it's always a range, even as close as 2100, and certainly the range grows by 20. Bruce pointed out, by 2050, we're pretty much locked into a certain amount of climate change, all right? And it's a small range, but the range gets really large near the end of the century. We could have like 2 feet of sea level rise by the end of the century, or 5 feet, and I've even seen an estimate as much as 15 feet because of all the uncertainties and what may happen in the ice sheets. So how do we think about design now? Because we can't use the old method of just choosing a design value. Because if we overestimate, let's say the 100-year flood, we're going to overinvest, we're going to spend too much. And if we underinvest, we're going to suffer a lot of damages. So what's the approach of the engineering community? Like, how do we design for this new uncertain future? So I'd love to hear some people in the audience what are they actually doing? Okay, in the academic world, we talk a lot about it, but love to hear what people in the field are doing to deal with the uncertainty. So any comments? Yes, please.
My name is Kanay Ulala. I'm a civil engineer. And lately, in last 20 years, the trend in the towns is tremendous on drainage design. And most of the times, they follow the intensities given by NOAA. But there are some rich towns. They have exceeded those limits. They have made their own town regulations that if 20-year storm is 6.3 by NOAA, no, you design for 6.6. So they're trying to protect because they're seeing heavier storms. But on the other hand, when we do the design and we do deep hole tests for seasonal high water table. Sometimes in areas you cannot establish from the soil analysis. You have to look at the regional well waters records, which is being kept by Corps of Engineers. And we see all the well waters on average, they're all below average for last 15 years. Now, I live in Acton Town, and Acton Town has water supply by shallow water wells, 300 to 400 feet deep. And 15 years ago, we had summertime irrigation restrictions every other day. Last year, they said only 2 days a week. So this is like the state overall mass is in drought conditions. We do see heavier intensities, but overall precipitation is not enough to raise the water table at average level. That's my observation.
How do we
But economically, my business has increased in drainage design.
anyone want, so yeah.
Yeah, I have a quick answer to the question about what we're doing with design criteria. Basically, the design criteria follows the money. If we have $1,000 to rebuild the bridge, we'll use the Freeman flood numbers from 1970. And if we have more money to build a bigger bridge, then we'll use the higher numbers that we're coming up with all of our new science. So really, the way we do it is we base our design criteria on the budget and on how much money we've got to do it. Because if we've got a small job that is important to be done, then we want to use a design criteria that allows us to put that job out and get it built for a low amount of money.
Thank you.
Thank you all for sharing, and thank you for the presentations today. I wanted to add a positive example to this, because I think watching this and being a resident of Cambridge, I see those maps and I'm like, oh no, what did I do? Where did I move? But long story short, I'm working on one project that's a dam and a levee raise project. And this question of what do you design to, what do you pay money for, especially with these very large construction projects and uncertain futures, it's hard to find funding to do that, and also to really, have confidence in saying, yes, spend hundreds of millions of dollars on this when you don't know. But a short answer is that for dams and levees, what a lot of people will do, Army Corps one in particular, will say, let's design the foundation of the dam or flood wall for the 100-year projection, but will only build up to the 50-year sea level rise. So you're kind of cutting the cost of the total construction project, but you're not inhibiting yourself from doing that raise down the line. So everything, when you get to that future where something's more certain, you get more funding, you raise it a little bit higher. It's one example of how we can do it well and not have to spend an exorbitant amount of money now. Thank you.
We call it a robust solution. I mean, it works well over all the future climates. So incremental design, flexible design. Any more comments on how you design in the uncertain climate? Because we're all faced with this problem. Stephen, yeah.
So one of the things that occurs to me is a question of disclosure. So if we're designing the $1,000 bridge, are we letting people know that it's only a 25-year bridge and not a 50-year bridge? I work for the MWRA. The stuff I work on was built 150 years ago. And the stuff I'm building now is going to be around for 150 years. So having some level of disclosure about what assumptions you're building to seems like good public policy. You may not convince your decision maker to spend all the money, but you should, I think professionally, we're obligated to say, well, if we don't, here's the risk we face. And maybe you can build that incremental design, but not everything works that way. Some things it's either or. But I sure hope that folks are putting in their documents that they're stamping those disclosures.
Yeah, I really like that answer. And I will say that current legal action against fossil fuel companies does hinge in part on what's good professional practice by engineers. So if engineers as a group, it's good professional practice to not worry about these increases, that actually has a material influence on how things move through the legal system. So even if it weren't possible to always design for it, to acknowledge it as a matter of, professional expertise, I think is a non-trivial issue.
And I think as citizens, we can also advocate for our, if not our national government, our local governments to set standards. As engineers, we love to build to a number someone gave us, right? I mean, I can look around and tell you what the 100-year flood elevation was in a setup for a particular year, because the emergency generators are set 1 inch above that. I know the engineers knew that number because you can see across the building, right? Everything's set to that. If we can tell people that they ought to do something with a municipal mandate, Boston's starting to do that and making certain requirements. We take some of the decision making, the difficulty of decision making away from the specific consulting engineer. They simply have to do what they're required to do. So we as citizens need to push to get that requirement set conservatively enough that we're not going to have a deep regret.
Yeah. Thank you.
Yeah, and I guess on that note, I'll add one thing. My company does some of these like coastal protection projects, and I'm just a geotechnical engineer, not a coastal engineer. But one thing that I've noticed on a couple projects is that there'll be like a design for high frequency flooding and then a design for more lower frequency flooding. And so it's like maybe your solution for the high frequency flooding is going to be, installation of flood walls, whereas maybe the low frequency, more extreme flooding is going to be a bigger project kind of later down the road. That's going to be more encompassing, like the installation of a gate, across the 4-point channel. So I think almost from like a can swallow it sort of perspective, it helps to kind of have the solution that addresses the low frequency flooding and kind of handles that, and then the solution that might be a little bit more expensive and a little bit more encompassing and have the kind of low frequency project and just delineate them out that way. But I like the answer too about the adaptability and designing the foundations for something, or even flood walls for something that can be improved on later for sea level rise down the road too.
More comments on this? So more hands. Okay, so anyway, I want to thank you very much for attending. I want to thank Matt. I want to thank Bruce. And and I also want to thank Wentworth Institute for hosting this beautiful building. And also, thank the Freeman. Thank Freeman for all his great engineering he did, but also leaving the gift for this meeting. And as you know, this is an annual meeting, and look forward to seeing you all next spring. And have good summers. Thank you very much.